Okay, in this video I'm going to go ahead and continue on with LED response, or LED operation I think I called it. And what we're going to do is we're going to see what happens if we try to drive this thing too fast. Okay. So small frequencies at low frequencies means that we have the output response is linear. Okay, and we can predict the output power by looking at the input current. Okay. It turns out though that at high frequencies the output response dies off. So I'll just say dies out in quotes here. And what we have is that, remember we have P opt is equal to PDC plus PSP sine of omega t when I was equal to IDC plus ISP sine omega t. Okay, so this was the low frequency. And it was possible to predict PSP given ISP. Okay, where PSP is actually equal to delta P over I, delta I, that slope, times ISP. Okay, this is the slope of the response curve. It turns out that this output power magnitude, the magnitude of the sinusoidal part on the output, goes to zero at very high frequencies. And so when I say the output response dies out, what I really mean is that PSP approaches zero for omega approaching infinity. Okay, so we need an equation that captures that high frequency response. Okay, and there is an equation that we have that captures it very well and is based on a very physical picture of the time it takes for electrons and holes to recombine. Okay, so there's a certain amount of time gap between the time when, let's see, where's my picture? When electrons and holes are created in the p and the n regions and when they recombine to create a photon. And this is called the carrier lifetime. So we're going to call tau and this is more or less equal to the time between an electron and hole combining, being produced, and annihilation. Uh-oh. I don't know how to spell annihilate. Don't like to write things down. Let's see if I can find the word in the text. A-N A-N-N-I-H I-L-A-T-I-O-N. Sorry about that. Bear with me here. Okay, so this is time between the electrons, when the electron holes are produced and when they annihilate one another. And the photon is produced when they're annihilated. Okay, so it turns out that our equation is a very commonly seen one from the world of physics, where we've got things like this, where we've got some sort of a characteristic time giving us a frequency response, and we're going to see that P SP is equal to, well, the same delta P over delta I times ISP, but now we're going to temper that with a frequency response that looks like this: a 1 over square root of 1 plus omega squared tau squared. And you can see that this is a unitless quantity here, that at omega equals 0 it goes to 1, and that as omega increases we get a larger and larger number in the denominator. In other words, it gets smaller and smaller. So the plot of this looks something like this. Okay, so here's a 1, and this is the 1 over the square root thing, 1 plus omega squared tau squared versus omega. So it starts off at 1 and then goes to 0. Okay? And let's see, when omega is equal to 1 over tau, we get a 1 over the square root of 2. Okay? 1 over tau, and we get a 1 over the square root of 2, or 0.707, I think. And so that's the characteristic time. So this is a good model for the way these things behave, and this is the equation that we use as we study this phenomena. Okay, and what we're going to see is we're going to see that this is very closely related to our 3 dB frequency. Okay, we know that in optical fibers we could define an F 3 dB in terms of pulse spreading parameter tau. Well, now we have another tau, another time scale over which we have some sort of a response, and it turns out that our LED will have a 3 dB bandwidth also. Okay, we're not going to get into it too much. It turns out that our 3 dB bandwidth, I didn't leave myself enough room, F 3 dB is in a very similar arguments to those arguments we used with our optical fiber, is 1 over 2 pi tau. Okay, the other equation we're going to write down is that, well, you know, tau is not so easy to measure in a real device. If we have a real LED in our hands, we want to be able to make a measurement. Let me just start a new page, I guess. Okay, so what we're going to see is that the high frequency response gives rise to a 3 dB bandwidth that is 1 over 2 pi tau. Okay, where tau is the carrier lifetime. Okay, again, in a real device, carrier lifetime is difficult to measure. And what we're going to see is that what we can measure better is what's called the rise time, TR. Okay, and this is defined as the time to go from 10% to 90% of output when input is a step function. This is the picture in figure 6.9 of your book. We're going to have I, the drive current as a function of T, go from 0 to some value instantaneously, and we're going to have our P optical, our output, instead of responding instantaneously, it responds something like this. Okay, so it takes some time to respond, and what we'll do is we'll define, we'll take here's the 100% P max, here's 0, and we'll take from 90% to 10%, and we'll take that time as TR, T rise, okay? And it turns out, we're not too worried about all of the detailed analysis, that the F, the 3 dB bandwidth for the LED is something like 0.35 over TR. Okay, so it's very closely related to the carrier lifetime. Okay, and you can combine these two equations and figure out the response time in terms of the carrier lifetime. The carrier lifetime comes from the physics. The response time comes from actual measurements. On LEDs. Use TR. Okay, and the 3 dB frequency is the frequency at which the output amplitude has gone to only half of the input amplitude. So maybe I didn't really draw the picture again, but it's the same concept as we had in the optical fiber, where we would we would put a sinusoidal wave into the optical fiber, and out would come a sinusoidal wave with less of the intensity. So here's the, what am I calling it, PSP. So this is PSP divided by PSP input. Okay, and so this is a value that goes from 0 to 1, and as a function of frequency, well, let's just label it F now. We have something like this, and we have a 1/2, and this is our F 3 dB. So the vertical axis here is just or let's call it PSPDC. There you go. Okay, so here's the actual signal power divided by the signal power at DC, which of course goes to 1 at frequency of 0, which is DC, and then goes down to half at the 3 dB frequency. Okay. Hopefully that explains it. Thank you.